Ever turn on your kitchen tap and catch a faint whiff of a swimming pool? It's a very specific, sharp chemical smell. Before we figured out how to safely treat municipal water supplies, a simple glass of water carried severe risks. Pathogens causing diseases like cholera and typhoid swept through communities, routinely filling hospital wards. Today, approximately 98% of modern U.S. drinking water systems use chlorine chemistry to eliminate those exact bacteria and viruses. That faint chemical trace you sometimes smell at the sink is the literal barrier keeping historical waterborne plagues out of your home. But the chemical we rely on to make our water safe to drink is highly reactive and on its own, highly toxic. At room temperature, pure chlorine is a corrosive greenish-yellow gas with a harsh, suffocating odor. It's also heavy. Chlorine weighs about 2.5 times more than normal air. If released, it sinks and quickly pools into low-lying areas. This creates a massive logistical problem for city infrastructure. Engineers have to take large volumes of a heavy, deadly vapor, handle it safely within populated areas, and systematically use it to purify the water we drink. The process starts inside industrial water treatment facilities. To effectively move and store chlorine, chemical suppliers cool it down and compress it until the gas condenses into a clear amber liquid. It arrives at the plant inside heavy-duty 150-pound steel cylinders or massive 2,000-pound ton containers. Plant operators handle these storage areas with extreme caution. The tanks sit in isolated, sealed rooms positioned on the downwind side of buildings. Anyone working directly with the valves wears full chemically resistant gear and self-contained breathing apparatuses. Locking the compressed liquid safely inside a steel tank is straightforward. The actual engineering challenge happens the moment you need to pull the chlorine out and mix it into the water. When released, liquid chlorine instantly vaporizes, expanding to 460 times its volume. Pumping this rapidly expanding gas through pressurized pipes creates a severe hazard. Even a hairline crack acts like a high-pressure nozzle, spraying toxic gas outward into the facility. To prevent this, water plants use vacuum gas dosing systems. They rely on a Venturi nozzle. Rushing water generates a strong vacuum, pulling chlorine gas directly into the water stream. Because the pipeline is under negative pressure, the system protects itself. If a pipe breaks, no gas escapes, ambient air is sucked in. By forcing the system to rely on a vacuum rather than positive pressure, engineers use basic physics to neutralize the threat of massive volumetric expansion. Equipment is also built with hardware failsafes for external environmental hazards, like fire. The chlorine cylinders have fusible plugs engineered to melt between 158 and 165 degrees Fahrenheit, safely venting internal pressure before the heat causes the tank to rupture. If a large-scale leak does happen, facilities activate mutual aid networks, like the Chlorine Emergency Plan, bringing in highly trained hazardous material responders. When responders reach a leaking cylinder, they roll it so the puncture is at the top. Gravity forces the liquid to the bottom, meaning only gas escapes. Venting gas is manageable, but spilled liquid immediately multiplies its volume 460 times into a massive cloud. When primary machinery and reinforced valves fail, knowing exactly how to manipulate the simple physical states of the chemical provides the ultimate layer of defense. Once the gas is safely dissolved into the plant's water supply, it travels out into the expansive municipal pipeline network. Engineers calculate a tiny, precise amount of residual chlorine to remain active in the water. This continuous microdose actively fights off pathogens in the dark, miles-long journey through city pipes, which brings the perfectly treated, clean water all the way through the final miles of pipe and safely to your home tap. That faint trace of chlorine you catch at the sink is the sensory proof of a tightly controlled, highly engineered cycle that successfully controls a deadly gas to keep your drinking water safe.